Welcome to CSC 226, Programming Languages. This is your Associates in Computer Science capstone course. You will use the skills and concepts that you have mastered in your other CS courses and discrete mathematics preparation and apply them to the study of high-level programming languages. We'll look at their designs and their implementation issues. The course requires a high level of scholarly maturity, as you are asked to research languages that are new and different to your previous work, as well as work in teams to communicate and share your acquired knowledge. These notes are on Part 1 and Overview of Language Paradigms. Computing languages are categorized in different levels. Low-level languages are deemed computer-friendly. These consist of machine language, which consists of binary codes that correspond to the signals that the hardware components understand. Isn't it fascinating that regardless of the instructions we give to the computer, it eventually is just translated into binary digits 0 and 1 that represent voltage either being applied or not to a particular pin on a hardware device? That realization never ceases to amaze me, how our abstractions communicate with the hardware of computers. The second type of low-level computing languages consists of assembly languages. As many of you have studied in computer organization, these are the specific mnemonic instructions that are designed for a particular platform. Hence, RISC or RISC architecture versus CISC, complex instruction set architectures, have different assembly languages. This explains why software designed for one type of computer is not seamlessly compatible with the other. Now, Java managed to bridge this gap a little bit in the late 1980s by introducing the use of a virtual machine for each type of platform, so that its language could truly be write once and run anywhere. This was a huge portability issue, and we'll talk a little bit more about this in a later slide. The focus of our course, though, is on high-level languages such as Java. These are human-friendly languages. Now, I suppose you are saying to yourself, really? Human-friendly? I don't know. I have spent many hours fighting to get a few programs to compile and execute correctly, and it sure didn't feel human-friendly to me. I hear you. So let me qualify that statement. Human-friendly means we can express our logic in terms of English-like code, in a very abstract way compared to the low-level languages that the computer requires. It is hard enough to find brave, willing souls such as yourselves to program in high-level languages, but I suspect you would all run for the hills if we asked you to code everything in binary. So, to prevent you from running away, we will stay focused on high-level programming language paradigms. We will examine the features common to most languages, such as data types, control structures, subprograms, memory management, etc., as we compare and contrast the different implementation styles of different language paradigms. We will be using more modern languages to do this. For example, web languages such as XML and Python, we will practice with C# GUI. One other issue that I want to thread through this course is security. This has become more and more important as technology has developed and spread. So we will talk about security issues throughout the semester, recognizing that most of the standard languages are old, and security was not much of a concern when they were developed. To date, your skills have been based on using imperative languages. You have designed and programmed both structured and object-oriented solutions to problems. This semester, we will expand that knowledge to include scripting, GUI, and most importantly, functional programming languages. Functional languages are very different from the imperative style of designing and programming solutions. We will also consider the logical paradigm, using more modern logical applications of XML. Your textbook has a full chapter on Prolog, which is the traditional academic logical language often featured in a course of high-level programming languages. We will discuss the commonalities and differences and take a more contemporary approach to the material. In case you are thinking that you are perfectly happy just coding in Java and think you can manage any problem using it, let's consider why it is useful to study different language paradigms. First, it will improve your ability to develop effective algorithms. It'll improve your skill with the language you already are using. It will increase your vocabulary of useful programming constructs and help you choose an appropriate programming language for a given application. It will make it easier for you to understand and learn new languages. And finally, an answer that I believe you all can relate to here is it will make you more marketable. If we take a look at job listings, here's one for a junior C#.NET developer, we'll notice that it is rarely the case that there will just be one language listed. They're going to want you to know different skill sets. Here we see .NET C#, which we will take a look at, some SQL, RDBMS, platforms with SQL, JavaScript, jQuery, Ajax, Bootstrap. So looking at some of these job descriptions, it becomes an alphabet soup. But once you have some background in some different programming languages, it will give you confidence to learn others and also make you more marketable. When I looked through these jobs earlier, I couldn't find one that just listed one language skill. Not one. So from a practical standpoint, you will obviously need a broader skill set than just saying, I can program in Java. Now let's consider the attributes of a good language. A good chart to review is on page 7 of your textbook in terms of the criteria for judging a language. Conceptual integrity. This covers the clarity, simplicity, and unity of primitive concepts. Is the language easy to read and write? Can you read through that code and figure out what's going on? Orthogonality. This is the ability to combine various features of the language in all combinations, with every combination being meaningful and consistent. This is a hard concept at first, and honestly, I think you could argue in favor or against the orthogonality of any language. So as you're studying and thinking about languages, look for exceptions to the rule. Where are there inconsistencies in the language? And this is kind of easier to spot as you're trying to learn a language. Why do we consider this a good thing? Consistency is always a good thing in a programming language. How well does it support abstraction? This is important for humans to be able to tackle more complex tasks. We will see that the functional languages really shine in this regard, and many of their fundamental constructs have been adopted by the popular imperative languages in recent years. Ease of program verification. We need to always strive to write well-designed, reusable software for most applications. If we can verify the correctness of our code, then we can confidently reuse it. And this is part of why testing is so important. Another important note to consider regarding software verification is that many of you will be working as software engineers in the future, and you will be tasked with writing applications that are mission critical. Lives may depend on the correctness of your code. Autonomous vehicles, defense systems, air traffic control, medical devices. All of these programs need to work correctly 100% of the time. So keep that in mind and strive for perfection when you write your programs. Here are some more attributes. Portability. Portability has to do with when an application is written on one type of computer and needs to be moved to a different computer? Can I just pick it up and run it on a different type of computer? Now, more of the modern languages support this, but they do it by being interpreted languages, and we'll talk more about that in a future lecture. Java, claim to fame back in the late 80s, was the fact that it was a portable language. I could take a program written on any machine and run it on any other machine, provided it had the Java runtime environment. This isn't the case with a language like C++. And we'll talk more about that when we get into data types and the differences of Java and C++ under the hood. The cost of use. This can be examined in terms of execution and speed. Certainly an executable language is faster than an interpreted language. Translation, program development, maintenance. How hard is it for programmers to learn? What is the cost to a company to pay for the software or train their programmers? All of these things fall under the cost of use. Security. Now, I want you to think about this a little bit. Languages that you have already studied, such as C++ and Java, have some security weaknesses, and so do other prominent languages. If you know about them, I would like you to add a starting discussion thread to the Week 1 open discussion about this. So brainstorm a little bit. I think you could probably quickly come up with a C++ security issue, or C and C++. Maybe not so quickly with Java, but you studied this in data structures, and even one for Python for those of you who know how to code in Python. See if you can spot a security weakness and post it in the discussion forum. Finally, good choice decisions are also based on the programming environment and naturalness for the application. You could probably code anything in Java or C++. It may not be the best choice based on your environment and the application that you're trying to write for. So it's good to be versant in several languages, and large-scale software today is rarely just done in one language, unless it's a particular embedded system or required for a particular reason. Here are the four major paradigms: imperative, object-oriented, and you're familiar with both of these. The functional is new to you, and the logical is probably new to you. Styles include a language that's compiled, linked, and then an executable is built. These languages have certain characteristics that are different from an interpreted language. And the different types of applications. We want to keep that in mind as well. These have an influence on the style and choice of language we will make when we're completing the application. Is it a mathematical, scientific type of application, or is it document-driven or data-driven with a lot of transactions going on, transaction processing applications? AI, artificial intelligence applications? Or is it multimedia and internet-driven? Let's dig in a little bit into the details. The imperative paradigm is command-driven or statement-oriented. It's based on the machine's state, the set of all the values for all memory locations in the computer. It's usually done sequentially, and it's very algorithmic-driven. Languages such as C, Ada, BASIC, COBOL, Fortran, and even structured C++ follow this paradigm. The object-oriented paradigm is based on solving problems by focusing on cooperating objects. The languages Smalltalk, Java, C++, and Eiffel all come to mind as leading object-oriented programming languages. All these languages adhere to the von Neumann architecture. A program consists of a sequence of statements, and the execution of each statement causes the computer to change the value of one or more locations in its memory. That is, to enter a new state. The functional style takes a different approach. It is more abstract and is not tied to the von Neumann architecture. It's also referred to as applicative. Program development is based on functions that the program must execute to achieve a desired result. The focus is on functions and the use of recursion. Prominent languages include Lisp, Scheme, ML, and Haskell. And newer functional-leaning languages, F#, Clojure, and Scala. The logical languages are rules-based languages. These are based on predicate logic conditions. They are executed by checking for the presence of a certain enabling condition, and when it's present, they execute that appropriate action. These are outcomes-based languages. The order of operations to getting to the solution isn't that significant. It's often presented as a set of rules that, when applied, achieve an outcome, and the order of those rules are not necessarily important. Languages such as Prolog, which is heavily used in academics, and XML technologies such as CSS and XSLT fall under the logical realm. These feel really different from the style of programming we're accustomed to, but they fit specific applications extremely well, and as you study and learn and code using these different paradigms, you will expand your ability to solve problems efficiently. We will consider the commonalities of languages. We'll explore their sets of operations, such as addition, subtraction, multiplication, division, the relational comparisons, logical operators. Most languages share these features, but how they are implemented can be quite different, and some languages include others that we're not familiar with. Here are a few popular ones. The caret for power operations, and the in to check for membership in a particular data structure set. Now, not all of languages perform their operations the same way. For example, the C family of languages uses short circuit evaluation. Not all languages do. Visual Basic comes to mind. The data types. Most languages have specified built-in data types. You are familiar with Java's, but many languages include built-in data structures such as hashes, dictionaries, and sets. Java can provide you with these, but they're not part of the language. They come from the libraries. One of the legacy languages that you will be studying even has a built-in complex data type. Sequence control of operations are fairly standard for imperative languages, but not so for the logical languages. These three topics, data, operations, and control, will be part of the basis for much of what we study and compare in a variety of programming languages this semester. And of course, security issues will also be considered. So for follow-up, be sure to study and read and follow the Week 1 study guide. You need to carefully review chapters 1 and 2, and I suggest that you read the summary before the chapter, just so you have an idea of what's in the chapter. Focus on the suggested sections discussed in the study guide. Organize some team time with your cohorts for Project 1. It's posted, and the team assignments are already out there. And then please post to the discussion thread about a security deficit in a language that you are aware of. Happy coding!